Hey guys, today we're going to talk about how to find the maximum walking speed of a person, and then we're also going to discuss apparent forces and as well as apparent weight in circular motion. So, maximum walking speed. When a person is walking in a stride, all right, when a person is walking in a stride, they are undergoing circular motion in each stride. All right. So I want you to zoom in closely to this lady walking over here. As you see at the beginning of the stride, we're at point A. Let me use a different color for clarity. Yeah, it's a different color for clarity here. We're at point A at the beginning of the stride. And then in the middle of the stride, we're at point B. We're kind of lifted up a little bit. And then at the end of the stride, we're at point C. So because of this curve here, and we also have a radius, the center of our circle will literally be the bottom of the floor actually, not the bottom of the floor. So because we have this curve that's formed by the stride, and we also have a radius, we can talk about uniform circular motion. All right. So I just modeled it right here. I modeled it. This is my just model of what's going on. So this is A, B, C. So now we want to find the maximum speed she can possibly walk at. The maximum speed happens, in her case, at the top, when the normal at point B, and at point B we have no normal force because we're lifted up. So let's see, point A, we're on the floor, so we have a weight and we have a normal force. Point B, we only have the weight acting on us. The normal force is going to be equal to 0. Point C, we have back to normal force and the weight. Yeah. So now if we analyze our point B right here, we know that the x direction will always point, like if we analyze, the x direction will always point towards the center of the circle. That's true, right? The x direction will always point towards the center of the circle. So if this is my center and my weight is over here, yeah, then my forces in the x direction is going to be equal to, let's just A, B, C, it's going to be equal to my weight. And the speed I can find from this equation is the maximum speed she could walk at. So how do I find that speed? Well, I know I'm accelerating. So my F is equal to MAC, weight, and AC is going to be equal to V squared over R. It's going to be equal to, and weight is mg. We can divide both sides by m or multiply by 1 over m if you like. That's what I like doing. The m's will cancel, and then we're going to have v squared over r is equal to g. And cross multiply here. V squared is going to be equal to gr. And I can square root both sides. V is going to be equal to square root of gr. So that's our maximum speed. Yeah, so the context matters because there are times, as we'll see in this video, when the time when the normal force being 0 will actually give us the minimum speed. But here at the top, it's clear that we have during our stride of our maximum speed. So yeah, it's just one way to find the maximum walking speed. Anyway, all right, let's talk about the centrifugal force. Yeah. First of all, the one thing about the centrifugal force, right? The most important thing you should know about this is that this is a fake force. All right, it's a Fugazi. It's a fake force. All right. Here's the formal definition. All right. This is a fictitious force that makes an object an object feel as though they are accelerating in a direction opposite to that of the centripetal force, which is a real force. All right. So just to recap, when we are undergoing uniform circular motion, we have an acceleration pointing to the inward, pointing to the center, right? We have an acceleration pointing to the center right there. So that's under the acceleration is caused by the centripetal force. So Fc is equal to MAC. Now the centrifugal force makes us feel as though we're moving opposite to that. You know what I'm saying? But and which is it's actually very fake. You know, it's not a real thing. But yeah, that's just a recap. So an example of this scenario is we are moving on a sharp curved left turn. All right, like imagine this here is a car, and we're going on a left turn. All right, so I'm going to, so the what we feel, let's see, what we feel as though we are gonna get pushed to the left, right? We feel as we go along this sharp turn, we feel as though we are pushed to the left. All right, it feels as though I pushed to the left. This feeling is fake. All right, let me say this feeling is fake, comma. Yeah, this is the centrifugal force. All right, and it's not what's going on, but it's a fake push. All right, it's there, but it's there because we feel it. It's apparent. It's a fictitious force, but it's a fake push. All right. So back to my example here. So what's actually going on? You know, when my car here is driving, you know, when it like this, just imagine this is moving forward. All right. The car what's actually going on? The car is experiencing an acceleration directed at the center of the circle. So why do we feel the centrifugal force then? All right, why do we feel the centrifugal force? Well, we feel it because before we approached the curve, our bodies was moving. Our body was moving in a straight line, and when the car started to turn, the car pushed inward. The car pushed towards the radius of the curve it's turning along. And because our body resists acceleration to some extent. That's the law of inertia, the first law of motion. Because of that resistance, that is why we feel as though we're being pushed to the left, to the right. All right. Oh my God, I said left here. We're pushed to the right. Sorry. Push to the right because it's the left turn. Push to the right. So, as the car is moving to making a left turn, all right, this is what is truly happening. And then a person in the car would feel outward fake force. All right? That's what the person in the car would feel. All right? That's pointing to the right. All right. So the centrifugal force should not appear on your free body diagram. Never put the centrifugal force on your free body diagram. All right. Now, apparent weight. Let's talk about this. All right. So if imagine when I'm in a roller coaster, a moving roller coaster. This is my roller coaster, and it's moving in a circular, like it's moving in a circle, in a circular path. Yeah. So of course, undergo the velocity is moving. It's moving at a constant velocity. All right. Roller coaster. So moving at a constant velocity. So, and I'm moving in a loop. So I'm undergoing uniform circular motion. So yeah. So just by looking at this, you can tell I have a net force pointing to the center of the circle. So now at the bottom, let's try to find our apparent weight. And do we recall what apparent weight is? Really, the apparent weight is the weight we feel, all right? And we're able to quantify this, all right? We're able to quantify the apparent weight. And how do we quantify it? We solve for the normal force at a particular surface that we're on, all right? So here, we're in a roller coaster, and we're at the bottom. Let's draw a free body diagram. So we're in the vertical plane. So that means our x-axis, right? Our x-axis points towards the center. All right. So we have let's see. Sorry, apologies. X points towards the center. Positive x is this way. All right. So at the bottom, positive x will be that way. I know this is weird. So that's my coordinate system. And then y is just tangent to it. So now, what forces are acting on my my roller coaster at the bottom? Well, it's on a surface, so it has a normal force in the direction of positive x and a weight in the direction of negative x. So I can solve for the forces. F of x, next direction, normal minus weight. And in actual sense, the normal force here is much bigger than the weight force in actual sense here. So I should draw it like this. And this is because we are moving in a circular path, and hence there has to be a net force pointing towards the center of the circle. So if I keep going, I know I have an acceleration here, so my f of x is going to be mac, and mac is just mv squared over r. All right, n minus weight. And now I want to find the apparent weight, so I solve for the normal force. So normal force is going to be equal to mv squared over r plus weight. Now notice that this W here is our true weight. True weight. And this one is the weight we feel. Alright? It's what we feel, let's say, due to contact forces. It's a very true weight. Alright? So I can rewrite this equation here, just replacing the m. I'll say n is equal to w plus mv squared over r. I can call n my apparent weight. So my apparent weight, which is just the normal force, w plus mv squared over r. And this weight here is our true weight. So I can clearly tell you that at the bottom, my apparent weight is greater than my true weight, because my apparent weight here is equal to my true weight plus this mv squared over r, plus the centripetal force, basically. All right. So now if I go to the top, I have let's see. So the top is my coordinate system is different. So because I always have to, the positive x is always pointing to the center of the circle. So it's going to be where positive x is. And what's this? Okay. Yeah. So that's what positive x is. So, and it's going to be my positive y. But we know in y there's nothing going on. So, positive x, I'm on the surface, I have my normal force, but I also have my weight force, right? And then here, finish my drawing, it's r, and my net force is downwards. Yeah. So my free body diagram would look like, it would look like here my normal force, and I also have my weight force. So I'm just trying to put them together. My weight force, and they're both pointing in the same direction towards the center of the circle. So I can solve for the normal force again. I know I'm accelerating because I have a net force pointing down. So mv squared over r is going to be equal to n plus w, and n going to be equal to mv squared over r minus w. All right, that's what that's equal to. So in this case, I can write this as my apparent weight going to be equal to mv squared over r minus w. So here we can see that our weight apparent is less than our true weight. Yeah, because this weight here is our true weight, and then our true weight is we're basically negating from our true weight, basically. Is that correct? Yeah. So yeah. Anyway, let's analyze the top a bit more. Yeah. So just to reiterate, so here just putting our forces on this thing just for clarity. It's not a free body diagram, but it's damn close to it. Just here for clarity. It's just here for clarity. And this is our radius. Yeah. So we showed, if we analyze the top a little bit more, we showed that n is equal to mv squared over r minus weight. Yeah, at the top, right? But I want you to pay attention to this equation here. So this equation, all right? So there is a speed v, that would make mv squared over r minus w equals to 0. All right? If this v here, if this v, is going to be equal to n. If this v here is small enough, there's a point at which it will make n equals to 0. But now what happens at n equals to 0, right? Like, what happens at n equals 0? Well, so what happens at n equals 0? The only force acting on the roller coaster is weight. And we see it here, you know. We see it. If I just put this guy over here, if I bring back the dynamic equation of the forces acting on it at the top, and that I make n equals 0, f of x is going to be equal to n, not n is 0, 0 plus w, f of x is going to be equal to w. So now, when n is 0, all right? So let's see. At the top, when n is 0, comma, the speed an object is moving at is the minimum speed it needs to stay in uniform circular motion. All right, that's the minimum speed it needs. Any speed less, that's the wrong place to put a comma. Any speed less, it will drop. So it's kind of like when you spin a bucket of water around. The reason the water is not falling down is because of the speed at which you are spinning the bucket in your hand. All right. Same thing for a roller coaster. The reason that I guess you are buckled in, but if you weren't buckled in a roller coaster, which is very dangerous and should never be tried, there's a speed at which you can spin through the roller coaster and not drop. Now the minimum speed you need is when n equals 0. All right, so we can solve for this speed. All right, we can solve for this speed. Okay, we can solve for this speed. We actually just did half the job. All right, it's the same thing that we've been doing. So if I just rewrite this equation here, and I know I'm accelerating in this x direction, so f of x is going to be equal to mac equals omega. AC, I know AC is v squared over r. It's going to be v squared over r. And what's weight? Weight is mg. Oh, look, I can multiply both sides by 1 over m to get rid of the m's. So mass doesn't matter. Interesting. So v squared over r equals g. And I can cross multiply, and I get v is equal to g, v squared is equal to g over r. And then from here, I can square root that and get v is equal to square root of g times r. And that's, yeah, and that's here is called our critical speed. All right, VC, our critical speed, the speed required, the minimum speed required to stay in uniform circular motion is called the critical speed. And this is very important. And yeah, don't forget about this. Yeah. So, just to show you a quick question before I let you guys go. A motorcyclist in the globe of death, pictured here, rides in a 2.2 meter radius vertical loop. Yeah. To keep control of the bike, the rider wants the normal force on his tires at the top to equal or exceed his bike's combined weight. What's the minimum speed the rider can take the loop? Well, this is the same question that we just solved. Well, the principle, we got the principle right. We can start by having a drawing, the top. Then we have our bike there. Then we can see, we know we're in a circle. So we know what forces are acting on our bike. We have the normal force and, the normal force and the weight force, right? So, and this is all in the x direction because x is pointing towards the center of the circle. And we have don't forget we have an r there. So, sum of forces in the x direction is going to be n plus w. And I know I'm accelerating, so it's going to be v squared over r equals n plus w. And I can solve for, now I know that the normal force at the top, the minimum speed which the rider can take the loop is when n is equal to 0. All right, so mv squared over r equals weight. And I can do the same algebra I did just 2 seconds ago. All right, mg, the m's cancel, v squared over r is equal to g. I can go v squared is equal to g, r, and then v is equal to square root g over r. All right, and my g is just my 9.8. And then my r, what I told is 2.2. And I can plug that in. And then that's the critical speed or the minimum speed the rider can go through. All right. This is part 2. I hope you liked the video. I know it may have been a bit sparse, but I hope it was informative and helped you revise. See you in class whenever you see this video. Bye.